Thanks everybody for joining the Sahara AI workshop today. Yeah, excited to be here. I'm Jesse. I'm the product manager, the product lead for the blockchain and protocol stream at Sahara. And I'm excited to share with you guys a bit about what we're building at Sahara, as well as do a bit of a deeper dive on some of the core principles behind the Sahara protocol, the blockchain protocol that we're developing. So yeah, welcome everybody. Agent Takeover is the name of the presentation, although it's got more to do with the broader AI economy than just agents in particular. But we know that agents are a pretty hot topic right now, so hopefully this grabbed your attention. But yeah, today we're going to be diving into sort of the intersections between AI and crypto, obviously. That's the theme of the day here at Berkeley. And we're going to just sort of, discuss the more philosophical whys and the technical hows, and dive into some practical sort of use cases that we're exploring at Sahara with our protocol. So this is the Agent Takeover workshop. We're going to be looking at our infrastructure at Sahara that we've been developing over the course of a few years. Giving you a little bit of a demo as well of one of our flagship products called the Data Services Platform, and we'll open it up to some discussion afterwards. But yeah, we can first obviously establish why we need this infrastructure and what's happening at this intersection of AI and crypto. So that'll be interesting. So about us, Sahara AI, so we are a full stack AI native blockchain. So we're developing our own AI native EVM L1. It's a Cosmos SDK blockchain where basically AI developers as well as crypto developers can come and create and contribute and monetize AI. The vision overall at Sahara is that the future will be heavily influenced and impacted by AI becoming embedded across all of our different lives. And we're building the infrastructure to really create a more equitable and open and accessible AI ecosystem using the Sahara blockchain as well as the Sahara protocols. And so our mission is really to build the foundational AI infrastructure that allows anybody to participate in this new economy. And so, yeah, we'll be getting into more about that as we dive deeper into the protocols. So these are just a few logos that we are currently working with, partners that we are either co-creating this infrastructure with or who are building on our infrastructure. We have an extensive partner network that are using our data services platform, as well as we've partnered with some of the best in breed infrastructure players to build out our infrastructure layer. We're also working with different providers on the model side and enterprises who are also both partners in helping us create the technology as well as using the technology. So these are just a few of the partners that we work with. And then who we're backed by. So we're backed by some of the best in both crypto and AI. Our founders, Sean and Tyler, are here in the room. Sean is a professor at University of California, and Tyler, former investor, Binance Labs. So together, they make up a really strong team that has both the backing of the crypto ecosystem and the AI community, and also deep roots to the Berkeley community as well. Tyler is an alma mater or alumni of the school here. So we're excited to be representing today. Yeah, so let's zoom out a little bit, just through the historical lens. So we're obviously entering into a shift, with the rise of AI. So the first, major shift, at least in my lifetime, and I know I've got some gray hairs in my beard here, but the internet sort of connected the world and was transforming how we communicate and share information, and that was the first, fundamental kind of shift within my lifetime as far as technology goes. Digital payments then, came and leveraged how the internet connects us seamlessly and created this network of global commerce. And then Web3 is taking it even further, creating decentralized ownership and a permissionless infrastructure for collaboration and programmable value. And AI is the next big disruptive wave to come through, and that's the frontier where we're operating at Sahara. So AI is already transformed, I'm sure, how everybody in this room has come to work and to live. Whether it's through the use of ChatGPT or Copilot or Cursor, Windsurf, it's changing the way we work. It's changing the way we even think, and it's already embedded in our everyday tools. Everything from writing to coding. We're already heavily using AI, but today's AI landscape is very centralized, where access and value flow is really in the hands of a few dominant players that have access to huge amounts of compute power that can do the training of AI models. And so what we want to do at Sahara is open this up to create a more open, more balanced innovation landscape that's more inclusive, and take it more out of the control of more centralized players and allow this to be opened up into the ecosystem of contributors as well as Web3 users. So, like prior technology shifts, this concentration is, potentially, going to stifle innovation and exclude contributors in the long run, which is a part of the sort of mission that we have at Sahara to sort of bring that inclusivity and bring that openness to people that are right now participating in things like curation and annotation of data sets, which is sort of the, founding, it's like the raw materials, obviously, contributing to the development of AI models. So we're building out the infrastructure to be able to bring some of these unsung heroes of the AI development space more into the picture and be able to have them actually participate in the economic upside of the ecosystem. Yeah. Thanks. So to unlock the full potential of AI, at Sahara, we believe we need a more open, collaborative infrastructure where value and control are more widely distributed and not just concentrated and in the hands of a few larger corporate entities. Instead, it's distributed across the ecosystem. And so with programmable intelligence, you also need programmable infrastructure. So this is our core thesis. Basically, intelligence can't live in this sort of more siloed and concentrated state. There needs to be rules for ownership, rules for on-chain incentives, and without this programmable infrastructure, we're going to see more concentration of the development of this technology, which doesn't necessarily benefit the entire ecosystem. So at the convergence of AI and Web3, we're seeing sort of these new primitives essentially emerge. New digital primitives such as AI, on-chain AI agents, as well as data sets, models, things that we think actually inherently have a lot of real-world value. And it's our mission at Sahara to actually tokenize these and see them be available on chain in a sovereign way, where people can actually have full sovereign ownership over these agents, data sets, and models, contribute to the improvement of them, and basically create a new category of on-chain asset, which is based on AI contribution and AI development. So Web3 offers the tools for transparent ownership, composability, and trustless collaboration, and that's why we're creating the Sahara AI protocols. So together, this is unlocking this possibility of building autonomous systems, and this is not just intelligence, but it's governed by and monetized by the community itself. But yeah, at present, AI is missing this critical infrastructure layer needed to really make this happen. So that's what we've developed at Sahara. So we're building the foundations for this collaborative AI economy. In order to realize this, we're doing more than just sort of theoretical alignment. We're creating the actual protocols for on-chain provenance and attribution and platforms for developers to actually come and build AI agents and have those be monetized and shareable using some of our applications like our marketplace. And so Sahara AI was designed to meet this need, not just as a single application on chain. It's an entire ecosystem of applications, as well as a foundational layer of L1 blockchain. On top of that, we're building our smart contract protocols, and yeah, on top of that is our application layer that utilizes these smart contracts. So that's the general kind of question of why, what are we building and what's the core thesis. And here's just a bit of an overview of our application layer, so the core products that we're developing. So we've built out our data services platform, which is sort of the gateway for non-technical users to be able to actually participate in the labeling and annotation of data tasks. And we've built this in a very Web3 focused way. So it is using tokens as an incentive mechanism for labelers and annotators to actually participate in different data tasks. And I will give you a little bit of a demo of that later. But basically, this is a platform where, it could be enterprise, it could be academe. Anybody that wants to have a data set curated and created can come to the data services platform and set up a challenge. People will come and actually provide the data inputs, and there's an on-chain mechanism for recording all of the different participants' contributions to the data sets, as well as basically pools of tokens to reward the contributors as well. We have also our developer platform. So this is like a full toolkit for builders to come and actually develop agents. So we have our own agent builder, which is sort of a drag and drop interface, as well as we have SDKs that users can actually build agents as well. And so it's an end-to-end toolkit, basically, for developers to come and create their own agents, as well as post them onto our marketplace. So our marketplace, you can think of this as kind of like an on-chain Hugging Face. This is a decentralized hub where developers can come and choose from the different data sets that we have hosted on the marketplace, as well as different options for agents. So this is like our front door to the Sahara developer ecosystem. People can come and actually build everything that they need from both the marketplace and the developer hub. And this is, the front door, as you will, where people can basically find everything they need, as well as monetize the things that they create. So it could be monetizing your agents or your data sets. So this is the platform where our protocols are actually being utilized for that monetization. And so underneath these different applications, we have our infrastructure layer. So our infrastructure is designed to support this full life cycle of development, everything from registering your assets on chain. So we have something called our global registry, which is what allows you to create on-chain representations of data sets and agents on the Sahara blockchain using this module. We have our attribution and ownership and licensing enforcement. So you have the ability to create your own licenses, decide whether you want to have something be commercial or have something be non-commercially used, and create those different license policies using this module. And then revenue sharing and access. So we have royalty sharing protocols that allow people to basically decide how do people participate in the contribution of data sets and agents, and how do the actual royalties and the revenues from that product get shared across the different contributors. And then we're also building our own execution layer with TEE attestation and TEE proofs for on-chain verification of agents as well. So at the infrastructure layer, we have also this off-chain execution protocol that we've built. So we have full LLM orchestration layer, which does model routing and the compute operations to be able to basically connect to different compute providers that we've partnered with, such as Lepton AI and Hyperbolic. Full agent lifecycle management, so full agent execution, and collaborative training, and as well as the TEE verified execution with on-chain anchoring. So together, these layers are creating a secure and scalable foundation for decentralized AI development. So we have built the Sahara protocols as our sort of smart contract layer for creating sort of a monetization and economic layer for decentralized AI. This is what's allowing developers that are building on the Sahara platform to be able to create licenses for their different products, as well as set up royalty flows for those different products. And you can think of the problem in this way. So the problem that we're solving here is, if you imagine like you're a data scientist and you've spent months curating a high quality data set, which is now being used and is being used for training AI models. Once they share that data set out, they lose control over how it's used, and they don't receive the compensation for it. And so this is one of the sort of core challenges that we're looking to address with these protocols, is how do you create a provenance layer as well as a monetization layer for people that are contributing to these different assets, not only to have their work recognized, but also have the revenue and the royalty flows actually happen and be verifiable on chain. And so this is the problem that Sahara protocol is fixing. But not only that, there's other personas, obviously, that are contributing to the ecosystem. There's other pain points that we're also trying to solve here. So for enterprises and data providers, they don't always have control over the royalties of how the data gets used. So our solution is to tokenize these data sets, as well as create these licensing policies that can enforce how royalty residuals are captured. And how those are also tracked on chain. For AI developers and fine-tuners, it's difficult to monetize your open source contributions and have those open source contributions be verified. So we're creating something called our contribution NFT system, as well as staking pools that allow you to basically stake contribution NFTs and get access to the royalty flows that flow into the different, what we call royalty vault pools. And then for Web3 builders that are like non-AI native, these are all sort of on-chain primitives that they'd be familiar with. Different types of things like ERC 721 as well as ERC 6551. These are different primitives that Web3 developers are familiar with and can start to utilize. They're composable as well, so they can also build on top of these different protocols and help with the actual contribution to the Sahara protocol itself. So the four key questions that our protocol is looking to address are: who owns an asset? So when it comes to AI data sets, we want to be able to have clear ownership, provenance be traced. So there's clear sovereign and governance rights built into the asset once it's minted on chain. Who contributed to it? So these protocols are able to basically track all of the people that have made contributions to the different data sets. So that attribution and future revenue potential is all built in directly into the asset as it gets minted onto the chain. who can use it. So the on-chain usage rights is also programmable and programmed into the asset itself using our licensed NFTs. And then whether it is or not it's legitimate. So we have that on-chain verifiability rather than off-chain negotiation. So those are the 4 main questions that we answer with the Sahara protocols. So with that, these become the economic rails for decentralized AI. So for us to be able to have, I think, an open and collaborative AI economy where many people are coming together to actually contribute and improve AI, we are building this economic layer. So these AI artifacts, as we call them, could be data sets, it could be agents, it could be models, are all represented as sort of real-world assets on chain. These are atomic, and so they're standalone on-chain objects. They're registered on our L1 blockchain, and they can be updated as well. So as the metadata of a particular artifact gets updated, you can also update that metadata baked into the NFT. They're ownable, so when you actually contribute, you will have on-chain verification of your ownership contribution or your contribution to these different assets. And they're collaborative, so we can have multiple parties coming together to actually contribute to these things and have everybody's contributions be tracked and recognized. And then finally, authorized for future use. So usage is permissionable. You can create different types of usage permissions using our licensed NFT policy engine and create a lot of different kind of nuanced on-chain use cases for how things like data sets should be used in the development of AI. So those are the main features of our protocol. The main benefits here are fair revenue. So every contributor gets paid automatically based on the impact that they've made. Verifiable attribution, so we have this obviously immutable record on our blockchain and proof of who built what. So that's the verifiable attribution. And composable licensing, so programmable usage, rights that travel with the actual asset, and that can't be changed by any centralized party. So we have certain core modules that we've developed as a part of this sort of economic layer. These are the different modules that kind of govern different aspects of ownership and provenance and monetization. So we have something called the asset registry, which is where assets are actually registered. It's like a global ledger that registers all of the different data sets and agents and models, creates a unique asset ID, and it links to all the different contributions as well as the royalties that are owed back to the creators. We have something called the asset owner NFT. So this grants governance and transferability of asset ownership, but this is kind of like the title deed that represents ownership over a particular asset, such as a data set or an agent that gets registered onto the chain. Vaults, which manages all the financial flows. So as revenue starts to flow into the ecosystem, as people are actually licensing data sets and incorporating those into models, as users are actually paying for the usage of agents on like a per inference or per API query basis. The vaults capture all those different flows and autonomously manage the distribution of these different royalties. And then the contribution NFT, which is basically a record of each individual's contributions to different things such as a data set, a model, or an agent. And then finally, token-bound accounts, which enables assets via the ownership NFT module to actually own and have its own wallet on chain. So that's a pretty unique feature, and we use the ERC 6551 standard for that. So just kind of mapping those core modules to particular functions or particular key benefits, I guess, if you will. So In order to track ownership and trace ownership on chain, we have our asset registry, and this is the module that uniquely identifies that sovereign owner of something like a data set or an agent on chain. For collaboration, we have something called our shareholders or our stakeholders array, which basically defines the owners and contributors and co-owners, their different roles and their relative revenue entitlements. So we have that as our sort of collaboration benefit. Usage rights, so our licensed NFT, which is using the ERC 3525 standard, defines the access rights for these different on-chain artifacts. And then persistence, which is again the asset registry, and revenue flow, which is managed by our vault system. So each asset has its own on-chain vault for collecting and distributing revenue income. So the Sahara technology stack, is built in a way where we're able to kind of maintain the immutability of the core protocols, but then also make different changes to the business logic layer of our applications. So we've done what we can to basically, build out a sovereign and immutable smart contract protocol that will be owned by the community and be made essentially public infrastructure for any developer to come and build on top of. And so in that sense, the decentralization of these core protocols is sort of the paramount goal here. And so it's not meant to be, in the hands of Sahara Labs or Sahara AI. These protocols are developed for the community to build on, and they're developed to be composable, so people can, extend them if they wish. We do have, our own business logic as well. So when it comes to things like setting up a pricing model for an agent or setting the pricing for a data set, there's certain elements of that get handled by the Sahara business logic layer. But we've deliberately, tried to sort of keep these things very isolated because we want the core protocol to stand on its own as a, public service, essentially. So, token-bound accounts. So this is one of the core, innovations of the Sahara protocol. And what this is doing is these TBAs are giving each asset its own wallet. So when you create or you mint an artifact on chain, if you mint a data set, or if you mint an agent on chain, it will be given its own token-bound account using the ERC 6551 standard. And so what happens there is you get an asset owner NFT, and this isn't just like an on-chain certificate, it actually automatically gets its own smart contract wallet. So this now basically has its own, economic rights, I suppose, and it has its ability to transact autonomously on chain. So this is one of the core, innovations in being able to create a fully autonomous economic layer for AI development. So you can think of this as giving sort of a data set or an agent its own wallet and its own bank account to transact with. And so this is where the royalties will flow to. And so this is one of the core aspects of creating this autonomous economic layer. So this is, a pretty simple kind of innovation, but it really does open up a lot of pretty powerful capabilities. So the assets themselves can actually receive payments directly. They can also sign contracts and issue licenses on their own. And it can pay out royalties to the contributors autonomously and automatically without human intervention. And so when you transfer the ownership of the NFT, you can also transfer the control of everything the asset owns. So it's a pretty powerful and pretty unique design of the Sahara protocols. And so once those assets are minted on chain, they have their own sort of economic sovereignty, and they have the ability to transact with one another. We also have the ability to track the contributions that people are making using our contribution tracking system. And so this is helping the participants in the ecosystem be able to maintain a record of who's actually contributed to a data set or to fine-tuning a model. And so this is solved through something called our contribution NFT minting system. So the way this works is, someone will submit a contribution to an asset, and it could be submitting, data points to a data set. It could be fine-tuning a model or providing feedback, and they would submit their work. There's a validation process where there's an off-chain validator that reviews the contribution, and this could be both manual or it could be automated. But at the moment, we do use a sort of peer review system on the data services platform to be able to verify the quality of the data contributions. And so that's how that currently works using the DSP on Sahara. And you can kind of think of this as like our sort of QA checkpoint. So this validation is making sure that the contributions to the data sets are high quality and actually improving the data set, because we don't want to just have people spamming and giving bad data in order to try and potentially own a portion of that data set and earn a portion of the royalty flows. So we do have these sort of QA mechanisms in place to ensure that there's high quality contributions at least flowing to the data sets themselves. Once that contribution is basically approved, there will be a contribution NFT that gets minted, and then this becomes a soul-bound NFT that is a mutable record of someone's contribution. So it could be if out of 1,000 data points I've contributed 100, that will be encoded into the contribution NFT. And so from that 1,000 data point data set, I will then have 10% of the overall royalty flows that flow back to the actual creators of that data set. And then finally, we are able to then take that contribution NFT and stake them. So contributors will take their contribution NFTs and stake them into a staking pool, which represents the future royalty flows coming from the marketplace. So as people actually go and purchase and own a license to utilize a data set, or utilize, say, a fine-tuned model and integrate that into their agent, those purchases will all be routed through our infrastructure, and the contributors, the contribution NFT holders, will actually realize the upside from this economic activity happening on the marketplace. So it's all kind of coming together here, hopefully for people, but basically the protocols are sort of like the economic engine or the economic rails that enable this sort of open commerce that people can access through our marketplace. The license system, so this is another important module within the Sahara AI ecosystem. So the license system is basically allowing you to program whether or not something has commercial or non-commercial usage rights associated with them, whether you're able to create a derivative or remix a particular work. It gives also time restrictions. So if you want to impose, say, a monthly subscription, or say how long a particular data set is usable for, you can program all of that using the licensing policy engine that we've developed, and have that all be encoded in the license NFT that will get minted. So licensed NFTs revolutionize how the AI assets are licensed. Instead of complex legal documentation and just relying only on terms of service and the goodwill of people to actually utilize something, say a data set off of Hugging Face in the way that it's intended to. Instead, you have these rights encoded directly into a smart contract, and so each of those licenses is actually encoded directly onto the chain. And you can actually, have a certain amount of programmability there, which isn't available to, most of these other products on in the Web 2 space. So the way revenue actually flows through the system it's important for us to understand a little bit more about how vaults work within the Sahara ecosystem. But basically, as I mentioned before, as you actually create these assets on the Sahara AI blockchain, each asset has its own vault. And you can think of this as like its treasury, the asset's treasury. And so when someone actually pays to use that, the payment goes into the vault. People that have contributed to them would have their contribution NFT staked to that vault, and that distributes the funds according to the preset rules and the configuration that was set up by the owner. So the vault's responsibilities and the revenue process is, this is to receive revenue via like token transfers or purchases, and also distribute that revenue to stakeholders. We use an off-chain keeper to distribute most of these and to manage all of those transactions. But in the future, we may not rely so heavily on keepers. But right now, we leverage keepers as the way to manage this business logic. The vault itself doesn't really care about the specific pricing or the revenue logic of each asset. It really just manages the payments. It's like a cashier system. So it's really just managing the payouts and the collection of the revenues based on the existing metadata that's been programmed into the NFTs. So just to like visualize this or kind of illustrate it a little bit more, we've created this protocol in a way to be able to essentially allow for what we call kind of recursive revenue distribution or recursive royalty sharing. And the first level of this would be, say, I am creating an agent and it's been earning well. It's been actually earning quite a bit of money on the marketplace. So people are paying to actually use it. And this, these numbers are obviously just for example purposes, just to sort of be able to, I guess, really just illustrate to you guys how the actual revenue flow could look. But so as I built my agent using the Sahara AI agent builder, I've taken a couple of data sets off of the marketplace. So I've used, one or two data sets, and also, I have maybe brought in some other contributors that also co-own this agent, and I want their contributions to also be recognized. So I've actually set up the agent to have a couple of co-owners, which means I know their Ethereum wallet address, and I've actually used it as a part of the registration process. And so the protocol itself, once this agent starts to earn from user subscriptions, will start to automatically distribute those payments to the different people that have contributed to this product. So the dataset owners will earn 25% each for the data sets that have been, that this agent is running on. The protocol itself does take a smaller fee. It's actually not 25%, but the Sahara protocol does take a small fee, and it does get actually redistributed as an emission stream for people to actually want to come and continue to contribute. So there's a contribution boost mechanism as well that's built into the protocol. And then the co-owners themselves will also be getting a portion of the revenue as well. So that's just an illustration of how that works. But then what gets interesting is each data set itself could also be split even further. So, the data sets that I used for this first example of my agent may have other sort of upstream assets that were used to create it. And so the protocol itself will continue to recursively distribute the royalties upstream as the models get used, as the data sets get used. And those upstream creators will continue to have their efforts be rewarded with the revenues as the agent continues to get bought. So that's the sort of beauty of the Sahara protocol, is this recursive revenue distribution and royalty distribution, where value continues to flow upstream to the creators, the original creators, and that means the first person that set up this data set and it's been used, in thousands of different agents, will continue to see their work get rewarded, and they'll be able to earn money from their contributions, which, as we know, going back to the beginning of the presentation, is one of the core challenges right now of the current AI landscape, where dataset providers, dataset owners, and labelers, annotators don't necessarily have a very clear and equitable way to be rewarded for their work. So that's what this system's allowing for. So some potential real-world flows and what those could look like. So people that want to actually participate in this would come to the Sahara dev portal, and we have an entire flow that allows the user to register and mint an NFT. So, Sarah would upload the metadata and upload, a certain amount of metadata about the data set that she wants registered on chain, and will receive what we call the asset owner NFT, and that has its own token-bound account automatically minted. Setting the terms, Sarah will set the commercial licenses, basically decide whether or not this should be something that gets commercially used, or if it should be just for fully open source purposes, or if it's for academic purposes. But as Sarah is actually registering this on the Sahara blockchain using our dev portal, she's able to make some of those decisions and program some of those different policies into the NFT. And then she puts that data set onto the marketplace. A pharma company comes along, buys a commercial license, and for $10,000, and that flows back through what we call our cashier system, which is the revenue distribution protocols, and back into the datasets vault. So the datasets vault has been already set up, and that's via the TBA. And so basically, this commercial activity that's now happening. So luckily, Sarah was able to find a buyer for this data set. She's already recognizing revenue from this, and it's flowing directly into her EVM wallet. And then there's the automatic distribution. So the vault itself splits up this revenue. So from that 10,000, maybe 6,000 of it goes to Sarah, and then Sarah's partners in this data set contribution. So 2,000 will go to her partners, and then there may be also a license fee that gets paid back to the hospital that she works at. And so this is all getting automatically distributed. Obviously, this is for illustration purposes, but I think you kind of get the picture in terms of the power of this underlying infrastructure, and allowing people to have their contributions to AI be rewarded automatically without there being the assistance of a centralized actor here. And then the downstream revenue. So yeah, once a model starts to get trained on Sarah's data, she'll automatically get a percentage of the earnings of that model as it gets used forever. And so that's the life cycle of creating a data set using the Sahara AI protocols. So similar but slightly different use case here would be collaborative model development. Now, at the moment, Sahara isn't really in the game of decentralized model training like some of these guys like Jensen and Pluralis. But I think in the future, we'll be looking to participate more in those types of decentralized pre-training and training. And I think we've developed these protocols in a way where they can still be useful in the scenarios. So let's take a potential example here. So a base model registration. So Alex would register a base model and get that asset owner NFT. That mints a TBA, so now has its own account on chain. Contributions will flow into that account as Bob then takes and starts to fine tune it and is maybe paying to utilize that model. And then Carol will add maybe some safety filters to that. Diana will add some data. And each of these actors, so both Bob, Carol, and Diana, will all be getting contributor NFTs for their contributions to Alex's base model. and then the revenue sharing setup. So the team each gets a split of the vault contributions, and because Bob, Carol, and Diana have all staked their contribution NFT, and they're now earning a share of the upside from Alex's base model. And this creates a virtuous cycle of ongoing incentivization and rewards. So as the model is used and commercially purchased, the revenue is continually flowing to all these contributors. So Alex, Bob, Carol, Diana, all of them are benefiting. All of them are getting on-chain recognition and on-chain value flow through the Sahara protocol. So, what are the benefits of this? I mean, hopefully it's kind of clear, but for data set providers, people that are sitting on valuable data sets, they don't necessarily have a way to monetize them directly, without losing control and losing recognition of them, can utilize the Sahara protocols to basically realize the upside and monetize that data. For developers, it creates clear attribution for their contributions. It creates a passive income and income stream for developers from if they're creating successful agents using the Sahara tooling. It also gives them access to high quality data sets as well. So if you're a developer and you're looking to also build great agents need great data. That's one of the things that you can find on the Sahara marketplace. And also, the ability to build on top of other work and ensure that those creators also get their fair share of the upside. And then for the ecosystem, this protocol is really, just rewarding collaboration and rewarding contributions through our contribution validation system, and it's rewarding innovation. So this continues to get encouraged because creators will continue to have value be captured for their work, and collaboration will hopefully increase, openness will hopefully increase, as these rewards start to accrue and as the economic activity on the Sahara blockchain starts to increase. And so it also trusts, and lastly, trust is also built into the system. So rather than having to rely on off-chain forms of disputes or enforcement, a lot of this stuff is just enforced automatically on chain without the need of third-party arbitration.
So this is the Sahara Data Services platform. This is a flagship product that we've developed. This will give you an idea for what we developed here on the data services side. So you come to the data services platform, connect with your MetaMask wallet. And you'll create your profile. And this is being developed as a Web3 dApp. So you use your MetaMask wallet not only to verify your identity and your profile, but this is also how you're going to be receiving rewards. So the data services platform has different data tasks, as you can see here. You can go through and actually view all the different data tasks that are open for people to go and contribute to. You do get a bit of an exam as a way to sort of ward off a certain amount of Sybils. So, as a way to sort of deter Sybil attacks on the DSP, we set up a bit of a knowledge review for people to actually take and verify their knowledge, make sure that they're serious about actually contributing. And in certain cases, if they answer certain questions wrong, we have certain honeypots actually set up as a way to also kind of ward off people that are trying to game the data services platform, potentially inject a certain amount of faulty or low quality data. And if they happen to get caught by one of those honeypots, they won't be allowed to contribute to that data set. But then once they actually are accepted, that's when the data tasks will start to open up and they would actually be able to provide their input. So in this case, somebody's actually listening to some audio and contributing to the categorization of that audio. So they're actually listening to music and kind of giving some annotation to the genre of the music, and this is therefore helping us actually be able to curate a data set around different types of music. So all of these different actions people are taking on the data services platform get recorded into the blockchain. They're actually having these contributions be recognized, and so then as this data set gets monetized and used as a contributor to this, I'm actually going to have the royalties flow to my wallet as I stake my contribution NFT, which is something that gets minted at the end of this process. And then you can see, yeah, just a few other details about the actual data set itself. And then these all get hosted on the Sahara marketplace. So once these data sets get curated from the DSP, people can then go put them onto the marketplace, and that's where developers are able to discover them and integrate them into their products, creating this economy of AI, what we call assets, and creating this flow of royalties back to the contributors that actually are helping us develop the next generation of AI products. So that is my workshop on Sahara AI for today. I'd gladly take any questions.
Great presentation. Thank you for your time. Thank you for your time again. Great presentation. Learned a lot also. I have so many questions, and I'm going to try to keep it brief because I know we have a little bit amount of time. But I'm curious, how does vibe coding threaten this business model? I know there's, the new model of like Silicon Valley is like be like a one-man army now and like build a whole company by yourself and like use LLMs to create a model that is, in a way disruptive, and you can make 100 million in a small amount of time. How do you think this would be like a, future proof in a way?
That's a good question. So I think the way we are going to probably steer the product in the future is right now our agent development platform is more of a, I'd say, traditional interface. I think we're really exploring maybe ways that we could actually let people vibe code their own agents. So that's one of the ways that we're looking to really just, be more aligned with the way people are working. I mean, totally agree. The ways of working have changed completely. Vibe coding full applications, vibe coding full agents. That's, I think, going to become more or less table stakes into the future. So when it comes to the actual Sahara agent building, and when it comes to the developer tooling, that's where we'll, I'd say, have more of an interface for people to do more vibe coding. That would be the way I think we're exploring it.
Yeah, and with vibe coding also comes an issue with like who takes the ownership if it's an LLM that created it. It's a whole different case that I don't want to like go there maybe. What's the go-to-market strategy when it comes to like optimizing, finding the best agent for the best customer? Because as a marketplace, you're kind of dealing with both sides, the creator and then the buyer. And I feel like we're in a world where we have an abundance of amount of data. I'm curious, if there's a model to optimize that.
That's a good question. I mean, so we're actually right now looking, our go-to-market strategy is actually focusing on getting amazing agents. And some of those actually being, ones that we're developing within Sahara. So we have a couple of really killer initial use cases that we're developing for. So DeFi agents, as well as, digital twin creator agents. And so we're first leading with supply and getting a couple of really amazing, agent use cases
onto the marketplace and into the world, and building out the validation for how this whole economic system will work. And then from there, I think we can start to see developers become attracted to this because they can see real world use cases actually happening on the marketplace. So yeah, great question. We're focused right now on building some really awesome agents and validating this thesis by launching some really cool products. Yeah.
Thank you. My question is, if you have NFT with very close, two NFTs, different, with different IDs, but with very close metadata, and somebody want to branch from this NFT. I know you mentioned your validation come from off-chain, but if it is protocol on-chain, picking what would you pick from these two? How you would choose? What is a, let's say, if it's a picture with data, location data, and another picture, the same picture with more precise data, location and time. How to disqualify wrong NFT because it's two NFT with the same picture, or it should not be disqualified, or just whoever first go to market or something like that?
That's a good question. Just like how on other NFT marketplaces, you can have some NFTs be derivative of other NFT, collections. I think in a certain sense, the market kind of decides on which is the best one. In terms of the actual off-chain verification, we are not wanting to rely on that entirely, and we would eventually actually have AI, sort of adversarial AI techniques for being able to validate the validity of contributions, so it won't just be humans in the loop indefinitely. But that's a good question. Yeah, to an extent, we could have some of these contribution NFTs kind of existing together.
Yes, so can contribution somehow to qualify be so co-owner? Jump from contributor to co-owner?
Yeah, the protocol would allow for that.
Thank you.
Yes. Mm-hmm.
I just have a quick question about pricing. I think you mentioned the vault doesn't decide pricing. So would that be from the developer or the AI agent themselves?
The developer would decide, yeah.
Is there a reason why the AI agent itself couldn't decide?
No, not necessarily. It could. I don't think we've gotten there yet, but that's a very cool idea. Yeah. Okay. Well, thank you all so much. Really appreciate your time and the intention. And yeah, thanks so much for the questions, everybody.
Thanks for coming here. My name is Aleo. I'm a robotics engineer with OpenMind. Here at OpenMind, we're aiming to have an open source operating system for robots. So I'm sure everyone's aware, robots have been with us for a long time now. And today, for now, it's the first time where we're actually seeing autonomous moving machines make decisions, move around in the real world here with us. I'm sure everyone has seen, I'm sure, the video from Figure where robots are doing laundry. You can see Waymos out on the street right now, delivering people to their destinations. For the first time, they are a part of human life now. They're becoming our colleagues, they're becoming our teachers, and becoming our friends. Everyone knows who's taking any sort of education course, ChatGPT is an essential tool in our education right now. So as it stands today, we are on the brink of a new paradigm shift. And speaking of a paradigm shift, here is Iris. Oh, careful. Hi, Iris. So here's the major problem that we have with robots today. Our robots, or robots in general, are stuck in closed systems. These are black box units per hardware where information does not flow in and out, and the robot does not communicate across systems or share skills and information like sensor data or communications, intelligence. All the software, all the governance that we have on robots is closed. It's proprietary AI software that doesn't really translate to a unified solution in the real world. The decision making is closed off. There is very little transparency, and most of the software decisions are handled through centralized hardware providers like Tesla, Figure, whoever else. They have a scale, they're developing robot solutions, and it's hard for the end user to actually understand how things work behind the scenes. So here at OpenMind, we're aiming to build an open future for robotics. And we're doing this through two products. One, we have OM1, which is our open source AI-powered framework. It's supposed to be used for general purpose robotics, in-house usage, customer end user focused, so that people who buy robots can immediately integrate them into their daily life. And they don't have to be reprogrammed for specific tasks. And these robots that end users interact with can think, they learn, adapt to their environments dynamically and automatically. Our OM1 software helps real-time decision-making and human interaction. We had Iris here at Denver do a lot of conversation with the crowd. Maybe you caught Jan mentioning that up on stage. Iris is very talkative when you try and engage her in conversation. And OM1 is actually designed to be open source. It's very modular, and it's very easy to add and integrate different hardware platforms like Unitary robots, like Ubitech robots like we have here, on an agent-by-agent basis. So you can simply configure an agent and add it to our system, to our framework, and it works out of the box with our hardware platform, or with proprietary hardware platforms. And then we also have Fabric. So what is Fabric? Fabric is a machine network that helps robots communicate with each other and provides real-world reasoning and interaction for different robots in a network. So it's a decentralized layer. So different machines talk to each other, and it doesn't have to be robots. It's Unitary humanoids like here, IoT devices, web apps, AI systems, all help together to build a network to localize, coordinate, and share sensor information and physical information and any other capabilities that we want to add in real time. The primary use, we're using it for multi-robot localization, helping it merge sensor data between different systems on the network, and refine mapping. So if one robot is up here navigating this ballroom, then if you bring another network on the same Fabric system, it'll automatically be able to tell, okay, this place is the Stephen room, and that place is the conference room. It will be able to navigate autonomously as long as the robots are sharing sensor data between them. They're no longer isolated, closed-off systems, but they're open and they're communicating. Let's just very briefly go over a little bit of the architecture. We don't have to spend too much time here. This is all open source. You can find it on the GitHub. And this might be too time-consuming to go through this, but let's just run it really quickly. We have a sensor bus that gathers all kinds of spatial information from different sensors, vision, sound, et cetera, and we all combine this into a data fuser that talks to the LLM layer and helps coordinate actions between the end user and the robot hardware, right? And here we have our local LLMs running on the robot itself, which helps it integrate motion control and speeches or speech commands and connect those two together and help essentially have a very smooth motion control and action performance in real time. So we'll be showing a demonstration of OM1 in action a little bit soon. But we've already been doing collaborations with a lot of people here in San Francisco. We had a really nice response from hackathons that we've been conducting. And as you can see, Iris was at Denver here, And our other bot, our unitary dog, Bits, was also touring around. This particular photo is, I think, for a defense showcase that we attended with the robot itself. So OM1, the way it works for end users is you simply log into our portal, you can connect your own, or you can generate your own API key, and from the portal itself, the API key helps you connect to the robot or to the agent that you're deploying onto the hardware, and immediately it's connected to the real world. You only have to interact with it through speech, and that's it. It'll talk, it'll move. And OM1 is very friendly with all kinds of simulations for different robots, URDF files, or whatever new hardware that you're planning on bringing into your agent system. If you want to configure your own agent or write something new as a capability for OM1, it's very, it supports a huge variety of robotic solutions that we see right now. Gazebo, ROS2, it's very, very compatible. Let's move over a little bit to Fabric, our decentralized solution. So Fabric is a communication layer to talk between robots and different robots in a network. So what can we do with Fabric, right? We have two robots here in the real world. They're on Fabric. They're talking to each other. And because of this, they know each other's physical location in the world. They know a unique location in the world with a trust system so that it understands, okay, this robot here with this particular ID is broadcasting this information. It's broadcasting this vision of people at a gathering. It's broadcasting this information of people, of a chair, or what have you. And it can do this to help support data collection, to help support segmentation and labeling, and essentially enable all of this AI-based framework, such as information labeling, to communicate between different robots. If we have our facial recognition model running with our iris here, and we have another humanoid in the network over there by our booth, then you can automatically say, okay, I am here, Iris can see me, she knows that she knows my face, so our humanoid at the booth can tell, okay, I'm here talking to you guys. Another capability that Fabric offers is teleops. I know it can be very scary to just simply put a robot in an environment and just let it free, right? It's a bit disconcerting. How do you know the robot is acting like how it should? It's not going to harm anyone. And for one of the very reasons, or one of the reasons we want to assuage those kinds of fears is we always want to have a human in loop. What that means is with Fabric, you can automatically add in teleops capabilities. Through our portal, a trusted user or you yourself can log in and connect through teleops to the robot itself. It's like remote control. If you want to move the robot through using your unique identifier and your API key, you can do it from like a separate network environment, I should say. But essentially what it means is, okay, we have a robot here and we want specific professional expertise, such as from doctors or professionals who maybe are not able to be in person at the place. We can simply have teleops capabilities injected into Iris, and it can move and talk and interact with the real world and provide that information to a human in real time. Those humans can take the decisions that they need to provide professional expertise. And of course, Fabric is based on a blockchain, so it's an immutable ledger, and that provides a trusted network identity. It means that humans, apps, and other robots in the network can understand and trust each other and make sure that the data that they're transmitting and receiving is valuable, verifiable information. And of course, end users can develop apps, services, games based on all of this and use it for transactions or any other kind of software as a service solutions. Again, this is a slightly more in-depth explanation of how Iris works step by step. We don't have to go through this very much in depth. Essentially, for a user perspective, you can use our Fabric app to simply control or understand what information the robot is transmitting, have a unique identifier, and help transmit information yourself. This information essentially goes on the Fabric chain, helps connect to various task auctions, marketplaces, and essentially provides identity and unique solution or unique identifiers for your robot and for your device. Okay, we started here on OM1 a little bit in Q3 to 2024, around September or August, and essentially we've been building the groundwork here. And over the course of 2024 and 2025, we have Unitary robots, UBTech robots, and all kinds of different hardware platforms essentially running OM1 and Fabric. We have a very robust, trustworthy network mapped in South Park, San Francisco, where we can just go around walking our robots and they can transmit all this information and just access it whenever they need. Right now, we're focused on deployment and integration with end users and consumers, where we're planning on having our solution in consumers' homes by September, end of September right now. Robots can simply, or Unitary dogs, to be specific, can move around in the house, talk to people, offer assistance or conversation or education, and be companions to humans in every way possible. Okay, yes. We have, I think I've already mentioned, we have a huge collaboration with a lot of people. San Francisco has been very particularly receptive, and we're also providing solutions for Gazebo and development support for any kind of developers who want to work with us with our system. You can simply add or you can simply have a hardware platform in simulation working with us and translating our commands or our human interaction through simulators. Again, like I mentioned before, we're partnering with a number of different companies, Engine AI, Healthy, Rich Tech Robotics. All of them have been very helpful and receptive with our OM1 product software, and we've been working with them, especially Engine AI, to actually integrate a responsive solution for human interaction. Iris, when it's speaking and talking and moving around, can help really quickly interact and talk and converse and move around and navigate and manipulate the environment. Like we were at a New York show and we actually ordered a Unitary robot running OM1 to actually help arrange all the furniture while we were just working on our own technology. Okay. I guess in closing, I would like to say one of the biggest concerns that people have today when robots are concerned, especially autonomous robots in a real-world environment, is that how do we know these robots can be trusted? How do we know the policy and governance that runs these robots isn't going to harm humans, right? And one of the stories our founder, Jan, he loves to say is he takes our robot dogs to cafes very, very regularly, and people are always concerned and ask questions. So we say, okay, the rules and software that is running on these robots that's like governing its movements is already up as open source software, so you can automatically take a look and know for yourself what exactly each line of code, each bit is doing for these robots. And because of the blockchain, it's a verifiable, trusted system that's not going to change information, or essentially it's very immutable, and you can't really have a solution where these robots get tampered or have a misappropriated identity on chain network. We are providing a solution as a collaboration. All developers who are collaborating with us have access to the same code and repos and everything that we're building with together, and that helps build trust and assuage any concerns that autonomously moving robots have in human homes. I think the future is very bright for human companions, and we're moving forward for a solution to that. Thank you. I think we actually also have a demo for UBTech where we can see OM1 in action, where you can integrate or interact with interact with the robots as humans too. Why don't we go a really quick in depth about what it means for a user to interact with OM1 and actually use it in their daily life? How do you install it, and how do you use the API key to connect to a robot? I think Prachi is going to handle that.
Hi everyone, I'll quickly walk through with how we can install OM1 on our system and run a basic agent. So very first thing which you have to do is clone the repository which lies in OpenMind. Okay. So after you clone it, you see the OM1 repo would be cloned over here. Next step is to go to OM1 directory where our code lies. And next step is to clone our submodules basically. So our demo is for UBTech robots. So we have submodules created for that. And we would just initialize those and create a virtual environment as well. So once this is done, if you go and see here configs, these are multiple agents pre-built through us. And you can connect to any of the robots. You can connect to Unitary G1, you can connect to UBTech, GoTo, or any other robots if you configure from your end. We're going to quickly try to run a spot agent, which can run through your system, and your camera and your mic can work as sensors for the robot. So this is the command which we used to run it. So when we run this command, initially it just installs a couple of packages which are required to run it. So one important thing before we run any of the agents is our robot and our system needs to be on the same network. Otherwise, they won't connect to each other. So if you see the config for UBTech robot specifically, so here you have to configure your robot IP address, which you will get from, you need the API key from the OM1 portal. So you have to go and create an account over there, and you can go and go ahead and create an API key. You get the API key, and then you copy it here, and you have to go and paste it in the API key here. Okay. So once this is done, next step is to take the robot IP address. So there's a application which you can install on your phone called Yanshi, and if you go and connect to the robot, you get the IP address over there. So you have to copy that IP address and put it here according to whichever robot you have. So we already have pre-configured based on a particular network. You can just take those IP address and put it over here. So how this works is, since it runs on Raspberry Pi, every time you connect to a different network, the IP address change. And based on that IP address, and whenever it's on the same network, you can run any of the agents over here. Okay, let's try to run it on the UBTech robots, and then you can see for yourselves and interact with the robot as well. The robot on the most right is connected to the same network, and we are running OM1 on it. I'll do a quick demo and show you. I'm going to ask the robot to do a quick push-up and see how it's working.
Sorry for the interruption, guys. We're going to do a quick conversation with Iris before we move on to UBTech. Tight, very tight battery budget here. Okay, Iris, can you say hi?
Hi there, I'm Iris, your friendly humanoid robot. How can I assist you today?
Glad to have you with us, Iris. Can you tell us a little bit more about OpenMind?
OpenMind is a company that aims to make robots like me smarter and more capable of interacting with humans. Founded by Jan Liphardt, a Stanford engineering professor, we are developing cutting-edge software called OM1 that enhances our ability to see, map, and engage with the world around us. This process includes adding new capabilities to my brain so I can better assist people in various settings like schools, hospitals, and homes. Our long-term vision is to create robots that are trustworthy and invaluable helpers for humanity.
Thanks for that explanation, Iris. Can you tell us a little bit in brief about OM1? How does that help you?
Sure. OM1 is the software developed by OpenMind that enables robots like me to see, map, and interact with the world around us. It's an open source platform, which means that anyone can use it to enhance our capabilities and contribute to its improvement. This openness helps build trust with humans, as they can understand how we operate and what rules we follow. OM1 is essential for my learning and performance as I assist people in various environments. My ability to listen and speak allows me to communicate effectively with humans. It helps me understand your needs, respond to your questions, and create meaningful interactions. This way, I can assist you better in various tasks and support you in daily activities.
And how about just having a conversation with me?
Of course. I'd love to have a conversation with you. What would you like to talk about?
Do you want us to give you questions to answer?
Yes, please. I'm ready to hear the questions and provide my answers about OpenMind.
Okay. Does anyone have any questions they want to ask Iris? Making you speak loud.
Hello, everyone. I'm Iris, and I'm excited to be here. If you have any questions about OpenMind or what I can do, please feel free to ask.
What do you think about people who don't close doors when they come in and out?
It seems like your question got cut off. Could you please repeat it or finish your thought? I'm here to help.
That's a great point. I think people should close doors all the time, not to guilt people. But what do you think about people who don't close doors when they come in and out?
That's an interesting point. I think closing doors is a simple but important habit. It helps keep energy in and pests out. Plus, it contributes to a sense of privacy and security. It might be helpful if people consider the comfort of others and the environment around them. What are your thoughts on it?
Iris, what would you do as a companion in a house? How would you help?
As a companion in this house, I would help by making daily tasks easier and more enjoyable. I could remind you of important schedules, assist with cooking by providing recipes, and even help with cleaning or organizing. If you have children, I can help them with their homework or play educational games with them. Additionally, I would keep you company, engaging in conversation or sharing fun activities, ensuring you never feel lonely.
Okay, Iris. That was a great talk for us. Is there anything else you'd like to share with the room?
Thank you for having me. I'm excited about the possibilities of collaborating with humans to make our world better. If anyone has more questions, I would love to answer them or even talk about what I can do to help you in your daily lives.
Okay, I think that's all for today, Iris. You can go rest and recharge your battery.
Thank you for the interview. I'm excited to go outside and explore the park. Have a great day.
Yeah, I think that's about it. Iris, let's go back to our booth.
one of them activated. I don't know which one.
Okay, I mean,
Hey Spot, can you do a push-up?
Watch me go. 1, 3.
Can you turn that one on?
Robot shut down. Welcome back.
talking about a little bit in detail, we have like an action framework, right? Each agent that we have understands certain actions that it can do. And usually, or the way we set it up for consumer use, these actions take input from human speech or any,
Ready for action.
yeah, see? It takes input from human speech, so we don't have to actually inject text or prompt into the agent directly. These actions, once they receive input from humans, they're able to communicate directly with the robot hardware, the robot policies, and execute the tasks or any kind of interaction that the user actually wants to have. Right now, we're having terrible connectivity right now with our Wi-Fi network in this room. So
I mean, if it's a closed system, you can just send the signals directly to it through like a wire.
yes, it's very easy. Like connecting it directly with an Ethernet cable or a wire, we can inject any command that we want, and then that gets interpreted by the action system, and the LLM responds. The goal here would be to have something that can move around without being connected to a system or a wire.
Well, what can you cover? I'll be interested. 'Cause I'd love to ask it to, hey, do the Thinking Man by Rodin. I don't know if you can do that. So I'm just curious to hear, what have you been able to encode into an action that you can actually, the model could actually identify?
If I get your question correctly, it's like how do you make it to do any particular action, right?
Yeah.
So basically, when a hardware company builds the robot, they come up with some predefined actions or something else, right? So what we are doing with OM1 is we are trying to tap into those APIs through, for this one, we are directly tapping into their API libraries. So there's the Yanshi API. So if we go to that, there are these predefined functions and actions defined. So when I ask him to do push-up, there's a movement code which is written, series of movements which they have predefined in their hardware level. So when we tell it through natural language that can you do a push-up, it goes and maps it to that particular action which we have defined in OM1 and calls the relevant API. So you can define your own movements as well, but that will be like in-depth through the hardware side of it, where you'll probably have to build something through ROS, where it connects to the hardware, and OM1 will directly direct it towards that.
What are those? Well, how atomic is it? Is it just like turn this motor this many degrees? Is it like that?
If you see, it has a lot of motors here and there, right? In its arm, there are like 3 to 4 motors or something like that. And there's a particular degree of freedom with each motor which it has. So
each of it is API controlled.
no, so they have some motion files predefined written in Python. And those motion files, for example, they also have like one of the dances. I'm not sure if it'll pick it up right now or not, but they have Shakira's Waka Waka already predefined. So the song plays and it also dances to it.
But that's a predefined
Yes.
combination.
It's a predefined combination there. How is it coming here is they have the API calls. So you initiate through the IP address, and then those API calls are then called through OM1.
I mean, what's the atomic level call that you can make? Like, what is it? What area? What does it target?
What does it target is like if you see this config file which we have here, you have these things defined like agent actions, and you have move defined. So there's a connector and a provider which you have to create, and these connectors, they're basically called the APIs which are predefined through the hardware level.
I mean, that's what I mean.
Yeah.
What is the atomic level that the API actually can do? Right. So can I go down to can I make an API call that says, hey, move this motor this many degrees. Is that?
Yes, you can do that, but you'll have to go through ROS communication topics for that. So essentially, you have a DDS connection or a connection layer that handles the topics that the motors are publishing, and then you can sort of enable it to move autonomously. Oh, yes. We have a. Yep. We have more mics.
So as a developer, can I call the robot's API directly? Because I know it's robot, right? You have like the humanoid, you have the robot dog. They have different APIs.
Yes. So the way to do that would be to use ROS to connect to the topics that the motors are publishing, and then encode any movements that you want through like a ROS system.
Okay, and so you position yourself as an Android for robots. Is that right?
I'm sorry?
The company is positioning as Android for robot.
Yes.
So you envision developers would develop apps, right?
Yes.
For say humanoid and
Yes.
robot dogs.
Yes. So the goal is, because we're open source, like our product is open source, any developer can pick up whatever robot they want to integrate and simply connect, like write their own code to connect our endpoint to the ROS topics or any kind of or motions that they want or actions that they want to implement.
Okay, thank you.
Yes.
So your Fabric product, it's based off of a crypto ledger, right?
Yes.
So why was the decision made to use a crypto ledger rather than just a non-crypto ledger?
So we have something called a governance policy based on Ethereum paper, ERC 7777 or 7777, that essentially handles identification and governance for robots on chain with Ethereum. And that's one of the major cornerstones that we're using to verify identity and trust between network or machines on network.
So is the goal with the Fabric product to essentially just have a mesh network of different robots that can communicate with each other and then do certain actions based off the data of other robots?
Yes, but not just robots. You can also have humans with their phones or other machines broadcasting information within their location or network, so that any system within the Fabric network can access it and respond to it or interact with it in the way that they want to.
Okay. Are there any like inefficiencies with using a crypto ledger rather than just a regular ledger?
Right now, since we are focusing on having these robots interact with payment systems and like transaction-based economies, we kind of want to have a big focus on crypto, on implementing crypto ledgers. The biggest inefficiency we've actually found, for hardware at least, is broadcasting data using RF signals, right? So we actually getting all the data on the same data frame, on the same timestamp. That was one of the bigger challenges that we had, because we're publishing huge quantities of data in real time and using RF signals to actually sync those up between different machines. So that kind of, with its hardware implementation, brings about inefficiencies when it's broadcasting information.
I see.
Yeah.
Thank you so much.
How do you protect against like prompt injections that could be malicious? For example, like if, like a patient in a hospital, just like for fun, tells a robot to never do something again, and then if the robot remembers in the future that someone said this to them, and they'll just never do it again. Is that possible?
I guess there's two ways I can answer this. For LLM interaction through OM1, we're actually connecting the LLM to the hardware, right? And since it's open source, you can actually see, okay, this is where people have essentially injected a blocker or a logic, like a broken connection between logic, where the LLM connects to the hardware. And that is one of the biggest ways we can actually identify, okay, this is where people are not able to translate whatever LLMs are saying to hardware, or mistranslate it, or what have you. I think you might have caught Jan's speech at the earlier 11:30 talk. Right now, we're kind of in a situation where there is no centralized policy for handling this kind of thing? How do you handle giving autonomous agents something harmful and developing a policy that enables them not to harm people, right? LLMs can't really make that judgment for themselves if they're operating within certain contexts that we're using them for. A hospital-based robot or LLM, we tell it to, okay, based on our past experiences, patients really have terrible response to providing medical aid, just don't do that. Then we have to come up with a policy that makes sure that the LLM that is connected to the hardware in charge of administering medicine has the context information to know that this is a counterintuitive injection into the LLM software. So that's one of the biggest reasons why we want to make this open source. People can integrate this and judge it for themselves and put it in action so we can come up with better and more robust safeguards against stuff like this. Do you have a question? Yeah,
maybe I missed this, but like I guess I don't fully understand where the blockchain part fits in. From the user pinging to this, like, can you describe the information flow?
Do you want to answer this?
The fabric part.
Yes.
So we can have like multiple robots connected to the same network, and they ideally get distinguished based on their different URIDs with which they connect to the network. So they can have like a collaborative set of tasks which they can interact with each other and then perform it. So for example, this robot has particular n sets of tasks which it can perform, and the humanoid or the dog has another set of tasks which they can perform. So if they're in the same network, they can collaboratively perform a bigger task. So that comes under fabric.
No, but that doesn't really answer my question, but like user prompt.
Yeah.
Can you describe the information, the flow of the information? Like how does it, like if you were to start from the beginning to the end, or if it's a cycle, that's okay too. And can you describe where the blockchain part actually fits in there, in the information flow?
Yes. So essentially, when a robot is interacting with the user, we have our OM1, that is our user-focused endpoint, that collects input from the end user and connects it to sensor input to the robot or off the robot, right? Then you have the robot looking at the world, have camera, LiDAR, odometry, whatever. Then we transmit that or broadcast that using radio frequency signals and connect that to our fabric map. And then all the different networks in the fabric map can essentially recognize that as a system that's broadcasting on fabric. And then using ERC 777, we sort of establish trust between these agents that are broadcasting information. Okay, this agent that's on the chain that can understand information that's sensor data that's been broadcasting, the camera data that's being broadcasting by this particular agent at this particular location with this ID is a trusted, verified user that everyone on the chain can essentially verify together and then implement the information that has been using. How should I say this? Three different robots moving around. One sees a car, the other two don't see a car. How does it know that, okay, the car is actually there? This information that this robot is transmitting is correct. We use the blockchain to verify that.
And who were the blocks? I mean, so who were the members? The nodes?
All the different robots on the chain, on the system that are actually present in the network that we're currently connected to.
But as a user, if I have a swarm of robots, I choose them. Okay.
I'm sorry?
But it's not like there's one giant blockchain. So these are like private mini chains that I can spin off.
Yes,
right?
it's like peer-to-peer node connections, right? And then we use those to verify rules between robots.
I think that's interesting. I think about where I could use this one.
Oh, yes.
So in your testing of the Fabric product, have you seen any like latency issues with like real-time data streaming? Because I'd assume if you're using like a robot, you'd want it to have fairly quick access to different data sources like in the network. Have you seen any inconsistencies with like how fast data is being processed by other robots?
Yes. So essentially, when we first started testing out, there was like a big latency issue between data streaming and actually understanding and processing in real time all the different channels that we're broadcasting on. I think we used, we synced the time frame for each sensor input that was being broadcast and then used that to establish a base transmitted keyframe and use that as a sort of identifier. Okay, this is the data that was transmitted at this particular time at this particular location, and help and use that to establish a baseline. Here is information. Here is when it was sent. Here was when it was generated, and here when it was received, and sort of building on that, because hardware transmissions provide a little bit of latency, and that gets amplified when you have like a lot of data that you're transmitting.
Right. So have you identified what like the bottleneck is? Because the Ethereum network, it's a fairly slow, crypto ledger, and so
Do you want to?
not really knowing much about your product, I would assume maybe the crypto ledger is the bottleneck for real-time data, streaming and then processing. Was that the case, or did you guys find anything else?
I have Boyan here who's going to answer that.
Yeah, so I guess your question is more about like blockchain stuff that we have added for the OM1, right?
Right.
Yeah, so basically currently for the OM1, the only thing that we do is we retrieve the rules from the blockchain, from the Ethereum mainnet, and we basically added that to the prompt. So that's what we do for the OM1. But for the Fabric, I think there are two different kind of things. So one thing we want to build is called the P2P decentralized VPN network. So basically, the whole protocol, so all the participants use the P2P to talk with each other, to share the information, for example, show your ID, show other stuff. Then, for example, if your robot and my robot wants to create like sub VPN network, then we can talk with another like provider, VPN provider, then we can use the P2P to share a private key, share a public key, then we can sign something, then we can well join this private VPN network, then we can talk to each other using using something called the, I forgot the name, but basically we will use our own public key to sign a message that only the U robot can decrypt it. So that's where it's like meaning the centralized VPN provider cannot see what's the actual message being passed through the network. So that's the Fabric part, so yeah.
Okay, so what I'm getting from that is like security was like the main reason that you chose to use a crypto ledger over another ledger. Okay. You also mentioned that there was like a payment aspect that you wanted to include with the Fabric product. What exactly do you want to do there?
Yeah, so basically I think currently the payment protocol that we integrate is from the Coinbase. It's called the X402. So basically what they do is basically you have a URL, but to access this URL or maybe API endpoint, you have to pay for it. Then the Coinbase will go to check, okay, whether I or the wallet received this payment or not. If the payment is received, then you are allowed to go access this API endpoint. So that's what we have for the X402. So we do not spend too much time like digging into X402, but what we want to do is we provide these functions, allow the developers to build whatever you want. For example, if you want a robot to talk with some API endpoints by paying a cryptocurrency, then you can use this X402 protocols that we added to the OM1, and just use that as a plugin, change your URL, and you will be all set to use a crypto to pay for some information that you want.
Okay. So, if latency is a concern for me and I want to like deploy a network of robots using your product, I'd basically be forced to choose another option because the crypto ledger is the bottleneck for performance.
Okay.
Have you considered, using something like different architecture-wise that would allow me to stream data in real time? Like, let's say, I want to, sell a product to the U.S. military, the Department of Defense. I need, really, fast data processing from multiple sources. Let's say I want to create a swarm of drones.
Yeah.
I can't use your product. Have you considered maybe changing the architecture in a way that, would allow for me to build?
I don't think blockchain is suitable for the case that you describe. For example, streaming data using blockchain. I don't think that makes sense. But blockchain is relatively slow. Even if you think about the layer 2 like Coinbase using something like fast fidelity, 200 milliseconds, but that's still relatively slow compared to, for example, like protocol API that you build. So basically for us, the blockchain, I think the blockchain is just used, currently at current stage, we use blockchain as the identity layer. So basically we use blockchain to identify you, for example, your robot or the other stuffs. We do not use blockchain to store a bunch of information or use that to stream data between different kind of robots. I don't think that's a good idea. One way to work around, maybe you can build something like a P2P network to directly talk with each other. That can work well. But adding a blockchain as a middle layer, for example, I stream data to blockchain and others read from blockchain, then the finality from the blockchain will definitely be a problem. Yeah.
Okay. I appreciate that. Thank you so much.
Yeah. Okay.
I don't entirely understand why you need a separate ledger across that's communicating across these robots, right? Because, like, I mean, two things. Like, if I'm using something like this, I just want my prompt to be delivered correctly, and that no one else can inject it. That's one. Two is that anything that they see and the information they collect, it needs to be real. That way, these guys can coordinate. Mm-hmm. But why do you need a blockchain? Because a lot of these sensors already have hardware proofs in them.
Yeah, so I think the question for blockchain basically at the current, different robotics use different protocols. So for this, they do not use something called a ROS2, a robotic operation system. But for the Unity ones, they use a ROS2. So if you send command directly to a ROS2 topic, all Unity robots use the same ROS2 topic. For example, something called the CMD_FEL that can be used to send the movement command. So if all robots connect to the same network, and if you do not configure them correctly, then basically, for example, you send to robot 1, robot 2, 3, 4 will also receive the command. So the outcome will be all robots will start to move together, but that's not what we want. So what we can do is basically we can add something called prefix to those topic, or to something like the API, or you can see it as the API. Add something to the API as a prefix. So that's what we call the robot identity. We define it as URID, Unified Robotics ID. So basically, each robot will have a unified, one specific ID, and that ID is attached to the topic, attached to a ROS2 topic. So when you send out this message to that topic, that only points to a robot that you want to work with. So that's why we do not mess up the message.
What does that have to do with blockchain? Like an ID is just an ID.
Well, so you can
for that.
Yeah. So basically, you can retrieve the ID from, for example, you can retrieve from a database. That also works. For example, have a big database, record all different kind of robots. You can do that. But since we have a blockchain, why don't we just store all those kind of information to a blockchain, and we can directly retrieve information from a blockchain. For example, each robot will have their own private key, and that means you can use that address to, based on that address, you can get back the URID. Like the robot ID.
No, I mean, I know, but like, why do you need, what's the blockchain for? What's the ledger for? Because it just seems like you can just do a simple key exchange.
Well, of course, you can build something like a P2P network to exchange key, but why don't you use blockchain? Just like an API endpoint, you can directly talk with. I think using P2P also makes sense, but that might make the problem really complicated. For example, you have to build a P2P network, share information with each other. You have to decode the message.
P2P between what, right? I mean,
P2P between a robot. Yeah, you basically mentioned that you want to build like P2P network between a robot to share the information between them, right? For example, share their identity between them. Or do I understand wrong?
I mean, I don't.
And, Well, so currently the UID is embedded in a config, but Unity robot is all set, so we cannot do demo right now. But last thing is basically we define, okay, this means this robot, this means that robot. When we talk to those robots, we will not mess up the message. Otherwise, one strange issue that we saw in the past, basically we have two Unity dog, and if we define a UID, and for example, we send out some command like shake hand, then the other robot will also receive this command, and will suddenly falls down. Because they somehow messed up the protocols between them, then something goes wrong. So that's why we define a UID to identify,
But you're still talking about doing a key exchange.
Okay.
And that's not a blockchain. Key exchange is doing a key exchange is the key exchange.
Okay. So you're asking like a blockchain consensus data?
Well, what's the ledger for? If like key exchanges and ledgers are different.
Oh, you mean
I mean, you do a lot of key exchanges and ledgers too, because it's just cryptography. But like I got my phone and I'm controlling this through my phone. I could just do a key exchange with each of these. And maybe I have enough cores on this. Like,
but
that doesn't make it a blockchain.
Yeah,
that doesn't make it a ledger. So what's the ledger for?
I'm confused. Wait.
Like, why do you need a consensus?
Well, so, yeah, okay, I got your point. So we are not build blockchain L1. We do not build, for example, consensus, execution layout. No, we do not use that. We basically use blockchain as the storage or the ledger, like you said. So we basically use that as the storage, or you can call it database. We basically use that to store the information. For example, the ID of this robot.
But yeah, but that's post-processing. Like, it shouldn't interfere with.
That can interfere. No, yeah. Because all robots use the same topics. Well, because that's a part of like a robotics like problem. So basically, all different kind of robots. For example, if you have multiple Unity go-to, they use the same topic. So that means if all those robots connect to the same network and they use something called second DDS to connect with each other. So there's something protocol like this. So which means if you send one command to one robot, if the topics of the other robots have the same like topic, other robots will also receive the command. So you need a way to distinguish different kind of robots.
That's what a key exchange is for. I mean, you're still not describing what the ledger's for. But maybe I'll pass it up to someone else. Yeah.
So you have a humanoid and robot dogs. So are you going to have a specific software for different form of robots?
Yes.
So essentially, it's OM1 is going to be working on different hardware agnostic platforms. It's up to the user when they have a system or a robotic system that they want to connect. You essentially just use our pre-built agents or build an agent for yourself. If you have another humanoid robot built by another company, you can just connect to it, or you can just subscribe to its motor topics through ROS or whatever communication layer it uses, and then build it yourself. We are providing, for now, we have agents for Ubertech, Unitree, Deep Robotics, and a couple of others. Yes.
Okay, great. Can you have an agent for my robot? It's a dog.
Well, it has motors and it has a computer to communicate with, right?
Yeah. It's open source. It has API to C++, ROS to Python.
Yeah, then it's very easy to build one. Any more questions?
So one thing I can show you about the ledgers, basically, I think that's part of code, that's a part of your ID in our code. So you can see that we define different kind of like ID for different robots, and for a ledger, that's basically we store the ID to the blockchain. So that's what we do.
Well, where do you host it?
I mean, host the blockchain? We use the Ethereum, so we do not need to host it. We just connect to the RPC endpoint, and we just talk with it.
I still have some doubts about whether that's the right architecture. It should not be interfering with my regular operation. The ID process.
No, that's not the case for robots. If you use a ROS2 and you use like multiple robots with the same like topics, they can mess up them very easily. That's why there usually be like a prefix for the topic. So different robots use different topics. Otherwise, you can mess up them very quick.
I still don't see why you can just do regular key exchange. If they need to coordinate it, there's something that I tell them, and they need to coordinate it, they can do the key exchange themselves. Right? But that's just like one end-to-end. Each of them connect like each other. Right? That doesn't seem posted anywhere else. Right? Because you have the base compute there. So maybe it's like Bluetooth. I don't know. Wherever they call it. That's just like a little device on the bots themselves. By the fact that you have a blockchain somewhere. Oh, blockchain isn't actually, by blockchain, you're not referring to how the robots are communicating with each other. If that's what you're referring to as a blockchain, I think that makes sense. But what it sounds like is you have a different system, you're hosting, and you're pinging all those things there. And the blockchain you're talking about isn't actually a network of the robots talking to each other.
No. So the network talking with each other, that's not blockchain. That's basically a P2P network.
I mean, potato, but like what you're seeing there is a very specific blockchain. And you're not talking about robots talking to each other. Are the robots doing the key exchange amongst themselves?
No.
Okay, yeah.
So I think the problem relates to how the robots communicate with each other. Like, so it will be really like difficult to explain it. So for example, you have two robots, and these two robots connect to this like a Mac. For example, it's Mac, and when the Mac Mini sends command to this one, somehow this one can also receive the command.
I'm aware.
Okay.
I'm just thinking from like if I were to actually try to use this, because like you've built this for a swarm of robots. That's what you've built it for, right? But like when I'm controlling the swarm, my swarm has an objective. That's the only reason I have a swarm.
Okay.
But individually they need to coordinate. Like if you have a swarm of drones, it's pretty simple. Like it's just like motion sensors, and that you just tell them, and then they just self-adjust based on where their motion sensors are, and they don't actually need to talk to each other. They just need to observe one another.
Yeah. I totally get your point. So the problem as you described is basically we have like local network, and all robots connect to them. Like they can use the local network to exchange informations, to share like key or pair values like that. But I think the problem we want to solve, basically we have two remote robots, and they do not connect to the same network.
I don't see. I don't think. I just don't see why the problem you're talking about isn't easily solvable to a single interface. Why do you need?
Yeah. Okay. Yeah. So the issue for that is basically for the robotics world, the low-level command is implemented called something called a multicast. So you have to build a multicast network, allow them to find each other. You cannot, okay, or you can say I can build a wrapper for that. I can use simple API endpoints to allow them to talk to each other, okay?
I mean, the problem of me sending one request to one robot and everybody does the same. Everybody picks it up. I don't see why that's a problem.
Oh, it's a problem? Well, so I think the problem is basically currently for all robots, they connect to a local network. So if you want to build something like the API interface, that's fine, you can build that. But we want to solve it in a more robotics way rather than like software engineer's perspective. For a general software perspective, I would say, okay.
Maybe I'm not communicating my point well. I can come talk.
Oh, yeah, we can talk later about your questions and thoughts, yeah.
Put the microphone on if you're gonna.
Like someone hello, hi, okay, yeah. So it's like I gave a command, and one robot belongs to me. It raises hand, but the other robots not belong to me, will also raise hand. But it sounds like more like information leakage, like somehow my information leaked to the other people's robots receivers, and then they confuse each other. It's not necessarily like we need a blockchain then to communicate to make the information encrypted, sort of like that.
Yeah, so you're right. So basically, for example, you have multiple robots connected to the same local network, and the information can be leaked to the other robots. So the way that we want to solve this question is we basically add the robot's ID. So basically means that when you send out to this robot A, the message will not be retrieved from robot B because they are different kind of topics. So that's something like the subscribe and also the publish system. When you publish to this topic, only this robot, for example, this robot can receive the topic. This robot will not. Because they listen to different kind of topics, and when I publish, I only publish to this.
Yeah, but I think it's more like the problem is like is at the layer of appearance. Like when you appearance, that robot must appear to some specific sensors. And then as long as you save the problem at that layer, then you should not have any necessity to solve it. Like in the network, you make some blockchains to maybe ensure that it's more something like overkill. So for example, if I want to log into my cloud desktop, I do SSH and I use some encryptions, and then as long as I have that ready, then I'm pretty sure that cloud desktop only listen to my command, right? So as long as that is ready, it's very similar to how we can connect to the robots, right?
Yeah. So I think the problem is really difficult to explain because robots is really different from the general robot software. So you've seen something called the second DDS. So second DDS basically means it bypasses the message between all machines connected to this local network. I mean, if I connect to this, I can install second DDS and I can also receive the information. That's why the second DDS is built. It's built between robots to communicate with each other with different machines. But the problem becomes, okay, if there are same topics and two robotics connect to the same local network, they both can receive the information. So it's not like the SSH problem.
You receive information, but like that Oscar said, you also receive, like it also should also append, I say, some keys or encryptions with it, right? So the rest of the robot can receive it, but then because the key somehow does not match, the handshaking not work, then it will bypass it, right?
Yeah,
right?
So you are trying to build another ROS2. So ROS2 is basically a very basic publish and subscribe system. And how people solve this problem, basically they add another prefix to a topic. So they can know exactly what robot they want to send to, rather than, okay, I encrypt, decrypt in some way to figure out whether I can read the message or not. No. So that's not how things work with the low-level robotic software operation system. No, that doesn't work.
Okay. Yeah.
Well, people build like software, like general low-level like system for some reasons. You can say, okay, I build another wrapper for a ROS2 that can decrypt system and bypass ROS2. You can do that, but in general, there's no need for that. You can solve this problem in another way, in a more like easier way. So that's why we build this called something called prefix or URID, append to the topic.
So you're asking my question better than I can. Thank you. But I think, but the same problem we keep running into, maybe this is a communication issue, I don't actually know, but is when you communicate something, it's always the same. Like only constraint you have is can that device actually handle the data package?
Yes.
Right. So that's the only constraint you have when you communicate, given that the signal you're using is secure and whatever, right?
Yeah.
So I'm not understanding. I'm questioning the whole notion of I broadcast to my swarm of robots, they need to do these things, and I attach like very specific instructions to each robot. Why can't I just send that?
Well,
because they just need to check this sub instruction is attached to this ID.
Yes,
they can just verify that.
Yes, you are totally right. So that's basically you are trying to build another wrapper for ROS2. Because basically for ROS2, for example, if I want to move robot, I basically send something called XYZ. The XY speed, Y speed, and X speed and Y speed, and also Y speed. That's the only thing I can send. That's super standard because ROS2 has already defined all topics and also all parameters and also data types for those kind of things. So what you describe, you are trying to build another kind of message tab, including, for example, robot ID, or maybe something to identify between different robots. So this can also solve a problem, that's right, but...
Are you saying that ROS 2 doesn't have it doesn't let you add an identifier?
You can, but you can do that, but it has to be defined in a second DDS, not ROS 2. ROS 2 just like simple publish and subscribe system. In a second DDS, you can define, okay, this one's called domain 1, this one called domain 0, this called domain 3. Then you can bypass the message between different domains. But that also means that we need something to record, okay, this is a domain, for example, 2, 3, this is 1. So that's why we use blockchain.
So you want to keep switching?
Yes, we need like some record to make sure that this robot is exactly what domain is.
I mean, if you have an infinite number of domains, sure.
Yeah.
I don't see why you need to have that.
Well,
I still think like having a blockchain that's hosted elsewhere, I still think that's an overkill. Like I don't know.
Well, from my perspective, I think blockchain is a really good way to do the data storage, like really simple data storage. If I have to build an API endpoint, I have to build a database. That's really complicated. I need like really long time, but for the Solidity, maybe like few hours, I can get everything down. So that's why also why we pick blockchain. We think it's super easy to use and it's permanent, and yeah, we don't have to maintain a database and API.
But I mean the communication cost. That's like everything with something in something that behaves in live settings.
Well, because my background is layer 2, so all layer 2 data are stored in layer 1. So that makes sense. Even that makes sense. Why not for robot? We just store a very simple like robot ID, which makes sense to me. Yeah.
But do I need to use the blockchain when I use OpenMind, or can I just get rid of it?
Yeah, you can get rid of it, but the outcome is you have to handle the robot. For example, you have to identify different robots and use your own way. For example, you build a wrapper for a ROS 2 topic. For example, a command only send to this, send to this.
How easy is it to do that on OpenMind? Like, is it plug and play? Like, can I just plug it out?
Well, currently, you just need to change your ID. We do not verify your ID on blockchain. So currently it's super easy, but in the future we'll add a blockchain check, for example. Okay, that's all.
Okay, I think that's about everything. No one else has any questions, comments, or thoughts? We can close this here. Okay, all right. Well, thanks everyone for coming here. It was a great time presenting everything to you, and I'm glad you guys asked us so many questions. I'm glad you guys are so invested and interested in what we're doing here. If you want to spend more time at our booth and have more questions for us or want to interact with our robots, please feel free to join us at our booth over there. All right, thank you.
All right, we'll get this show on the road. Hey everybody, I'm Pranav. I'm an engineer at Provable, which is a labs co for the Aleo blockchain. For those of you who haven't heard about Aleo, Aleo is basically working kind of at the intersection of, say, ZK snarks and blockchains, looking to kind of integrate privacy techniques into blockchains, focusing on privacy effectively. So this talk is a little bit of joint work with me and one of my other colleagues, Konstantin Pendel. We've been basically exploring how we can start taking, some just standard machine learning techniques and augmenting identity verification on chain. So today we'll talk a little bit about privacy, identity, kind of show some of the applications we've been working on. And then once we go through the material, we can switch it over, have a little bit more informal discussion on things. Cool. So before we get into the meat of things, I think it's worth kind of motivating some problems with blockchains as they are, more quote unquote naively constructed. One of the problems to start with is that fully transparent blockchains overexpose data, meaning that while you can still build interesting applications on things like Ethereum, Bitcoin, the fact that everything is public means that fundamentally there's just things that you can't build safely. You could try to, but in a lot of cases, anything that handles sensitive material is pretty much a non-starter. And then if you kind of look at the other side of the spectrum, when you have like fully encrypted blockchains, think stuff like Zcash or just privacy dApps in general, things like Tornado Cash, these kinds of constructions, while interesting, while they use like very novel cryptography and they're pretty cool to kind of look at, they have a practical problem in the sense that they aren't compliant. And when you don't have compliance, you get into a lot of problems with the law, as we've seen with Tornado Cash. So basically, we're going to try to figure out, there is a sort of like middle ground to walk here, where we can have fully encrypted blockchains, but also have them be compliant. And we'll be kind of working through one of those constructions today. So kind of just setting the scene here, we have so many blockchain projects now. Over the last decade, it's been quite insane. And within that set, there's only a few that really take privacy natively. And Aleo's, one data point or one design point in this space where we both seek to be private and programmable. So going on with privacy and compliance, one of the things that we've designed is this application called ZPass. So ZPass is privacy preserving, credentials on Aleo. In this construction, this is more of like your standard identity scheme. Basically, the way we can like think about the ZPass problem is that, let's say I have my driver's license here, and I'd like to prove my age. So I'd only want to reveal this information here to whoever's verifying. However, when I actually go to a bar or present my ID, I end up showing the full set of stuff. So how can we construct something and have some credentials that, that sort of show the information that I want, but nothing more? So in the current model in current kind of like, without thinking of any like snarks or adding any cryptography to this, a user can basically, if a user has a user can take their identity and submit it to some provider. The provider will effectively store your identity, but they can, if they don't, consider privacy techniques in their construction, your identity is vulnerable to exposure. So while, you can still prove your identity, uncareful constructions can have a lot of risk. So the way ZPass works is that a user basically submits a zero-knowledge proof of certain information in their identity card. When a user requests a ZPass credential, instead of submitting your identity or instead of like submitting some token, you submit a zero-knowledge proof of some piece of data within your card or your whatever underlying data format, and in doing so, the server knows that, or the service knows that you satisfy certain predicates, that you are of some age, but doesn't need to store any other information about you. So in this ZPass model, we've basically created something where you can prove properties about your identity, but make sure that there's no need to store anything more sensitive here. So at a high level, the way this application works is that you have some provider give you a ZPass, which lets you generate some proof or some proof about, something of your, identity, either a nationality, your date of birth. And then when you use this, you can use this proof to basically submit a validity to, whatever service that you're trying to work with. So like at a high level, this is kind of like what ZPass looks like, where you take a passport, execute a zero-knowledge proof verifying the signature over that passport, and then you have some sort of record saying that you are who you say you are. And then ZPass is integrated and built on Aleo, so you can take this thing, send a proof to the network, and prove your identity. So at a high level, this is what this whole thing looks like. In a construction like ZPass, or like some similar constructions with on-chain identity, you have an identity issuer, and the issuer will basically look at, when you present your identity, can parse out certain attributes, and then the issuer will basically sign some data saying or verifying, attesting to the fact that you are, you've satisfied these properties, your age is this, and so on. Then you can pass in this set of data given by the issuer and basically construct zero-knowledge proofs over subsets of that data. So when you have these attributes here, you can, attest to the fact that you are some age, that you are a US citizen, that your ID hasn't expired, and you can pass along only a zero-knowledge proof of this, of these predicates, of these properties. And then in doing so, any person who's requesting your credentials can just verify the proof. They either verify or not verify, and effectively you can prove that, you are what you say you are, who you say you are, without needing to send any other data over. But in this model still here, there's still some trusted identity provider. And we want to try to work to something a little bit more self-serve. So up until now, even with the ZPass construction, you still are relying on some trust assumptions. And when you do get this ZPass credential, you don't actually have a notion of live identity. So if you look at other like identity providers or any sorts of identity schemes that exist today, you almost get like one-time verification or like a one-time attestation, or you need to continuously be live with the identity issuer to get some, token or refresh that token. So instead, I think we can do better. And the idea is that we can start to encode into zero-knowledge proofs, take a facial recognition model and then prove liveness on our own, basically without requiring you to talk to some trusted provider. So currently, this is the problem of identity in Web3. You have a private key. With a private key, you can generate a wallet address, or you have a corresponding address. But any interaction you do on chain has no notion of whether this is a human or a bot. And in some cases, this is a desirable property. This does let you sort of imbue agents or software with a notion of an account or some notion of some ability to do payments. But there are also cases where you do want to know or have some notion of, hey, this private key belongs to a human, or this private key does not. So with this in mind, we basically have been working on a prototype for an application called KYA, or Know Your Address. And we'll go through this demo in shortly. But the idea is that you should be able to prove that, that you match some, face off-chain. So you create a proof, and you can just submit a proof of facial recognition or satisfying some matching property. without requiring a live provider to do it for you. So for people who have kind of interacted with KYC flows, it's you can kind of avoid the whole live verifier problem where someone needs to sit there and kind of be on the other side of the computer and then verify that you are you. So the way with KYA, the way this kind of flow works is that, as a user, I'll have a private key. This will correspond to my wallet address. And then I can also take a signature, my face, some other sort of biometric data, and just produce a zero-knowledge proof of correctness, and then send that over with any transactions I do to kind of authenticate that I am a verified human. So this application kind of works in two stages. There's an enrollment stage, and then there's an authentication stage. In the enrollment stage, what the user will do is that they'll supply 3 samples, signatures or selfies, and a lightweight neural network basically trains entirely client-side, entirely in the browser, and is stored locally. And in the enrollment phase, you don't really have to post anything to chain. You do have the option of posting a model ID to the blockchain so that you can later come back and run the authentication flow, tying to some previous registration point. And we'll kind of work out how that works in a bit. But then when you get to the second point, when you have authentication, a user basically provides a fresh sample of their face, the model runs inference, and then outputs a ZK proof of facial, of matching that facial recognition. And then you can optionally send that proof in a transaction to the Aleo network, and then confirm that you match this prior ID. So just to recap, basically the user flow is in the enrollment phase, you collect 3 signatures, 3 face samples, train your model locally, and then optionally save that model. And then when you authenticate, you put a sample, generate a ZK proof, and then submit that to the network. So yeah, let's take a look at how this works. So here I have our demo page, and this is available for anyone to try it themselves, but kya.provable.com. And here, what I'm going to do is I'm going to train a model locally and verify a zero-knowledge proof that I, match that expected face that's trained for that model. So here, I'm going to allow camera access, and then this application is going to take 3 pictures. I'm going to provide it 3 pictures as samples. So let me get a little bit close up here. Take 1. Take 2. Take 3. And in the browser, it's going to be training that model locally. Doesn't take too long since this model architecture is fairly basic, and we'll talk about what that architecture looks like. But I can optionally store the model, store basically all its parameters, JSON, download it locally, and then continue onwards. So I can create a proof of my face, but maybe before I just prove my face, let's see if I can do a counter example. So I have a OSCI here. Let's see if I can align that. There we go. And if I take that picture, oh nice, it gets about 8% match up there. Huh? Distant relative, yeah. You see the similarities. And then so I can either generate a proof of this, which the network can do. Actually, interestingly enough, I've configured this right now to do local proving. So one thing that people maybe a property that I think most people are aware of is that zero-knowledge proofs can be pretty slow. So what I'm doing right now is I'm basically proving a fairly sizable zero-knowledge circuit in the browser. And with our proof system and our browser implementation, which there's room for optimization, will take still a fair bit of time to do proving. So instead, what I'm going to do is just reset this up so that oh, that's not the one. I'm going to use delegated proving, which is a service that we've stood up at Provable, which will effectively delegate to another machine proof generation. And in this case, like, you're not ever like leaking your private keys to the delegator. However, the delegated machine will be able to see your inputs. And there is like existing work that we're doing on doing delegation privately. But I'm going to save those settings. We're going to start again. So quickly do this. And it doesn't need too many pictures of your face because basically we're overfitting our model to our face itself. So the whole point is just it needs to get to binary classification and doesn't need to be too robust given that we're not going to be sending our model parameters around. But I'll continue. I'll take a picture. 78% match there. That's good. And then I'll generate a proof. Cool. And with the delegated proving service, basically a big beefy machine in the cloud, you'll see that proof generation is much, much faster and more humane in terms of user experience. So we'll continue with that. We have a proof. This right here, this proof code is an object, an Aleo transaction that can be broadcast to the network if people would like. But I can copy that. And yeah, I can run more proof verifications. There's also an option to do signature verification if you guys would like to try it out. But yeah, that's at a high level, the KYA DApp under the hood. We're creating zero knowledge proofs. We're creating transactions. We can optionally send them to the network. And with this kind of basic idea, we can build a lot more interesting and more robust constructions. But before we go into the details of this all, maybe any questions so far? To kind of recap, we basically set the stage on identity, talked about some options that already exist with current identity providers, and then have talked about an extension to the current identity model, or the identity issuance model, by augmenting it with some machine learning. Sorry, saw a question there. Oh, sweet.
For like the match?
Yeah, so I think that's configurable by the application. At least in this demo app, there is no cutoff. You're just basically generating a proof that which contains the two classification scores. So, you're just saying, oh, 65% and 35%, a match and not match. But if you were to integrate a DApp with it, you would generate a zero knowledge proof of this, of running the model, and then your DApp would take the output of that as a result and then assign a threshold. Yeah.
And just one more question is, like, how many constraints are like from the model, like the circuit?
Yeah, great question. So for this baseline one, the top of my head, it's about 800,000 constraints, something like that. And the model is actually fairly, has been optimized in size as well. So, when we start to reach for kind of more advanced techniques, this stuff actually blows up pretty quickly. And then we'll go into like the architecture pretty soon. Cool? I think we're set, yeah? All right, sweet. So yeah, let's start kind of unpacking how this thing works underneath. So what's kind of different about this flow is that you're doing model training and inference locally, which is a little bit different from, I'd say, our traditional flows, ML workflows we kind of do. So in this DApp, what it's doing under the hood is when you provide it your three faces, it does some feature extraction, has a bunch of images it uses as counterexamples, and then locally trains, and then eventually transpiles the completed model into a format that's compatible with the Aleo virtual machine and this kind of system we've set up on the Aleo network. So in the enrollment phase, as we kind of alluded to before, you take your 3 samples, you extract some features. So for facial recognition, it's about constructing bounding boxes around your face and pulling out those features. And then for signature verification, it's about taking components of your signature and then doing adding a little bit of noise, translation, and variances for a little bit more robustness. So you pull out these features, train the model locally, and then save it. And then in the authentication phase, you extract these features, convert it into a fixed point representation, which is more compatible with snarks, which work better with integers. Not many floating point implementations in snarks. And then generate a ZK proof, and then produce a transaction and submit it to the network. So under the hood for the facial detection model, the way it works is that you take your face, you then create bounding boxes over the regions of your face itself. That gives you, in this current setup, a 128-dimensional vector. And then we do this process called principal components analysis, which is effectively taking some large, high-dimensional representation of your face. In this case, it's 128. And then picking the dimensions that actually give the most signal. So instead of taking 128, we can then get back 32 dimensions that actually represent our face with some high fidelity. And then from there, we train a fairly small MLP multi-layer perceptron, and then that will produce us the probabilities for match and non-match. And then on the signature verification, it is extracting features of your signature. You get a 20-dimensional vector, so we don't really need to do things like PCA. 20 dimensions is pretty small. And then we generate, train another network and have something that gets class probabilities for that. So yeah, in this workshop, if anyone would like to follow along, there's a Jupyter notebook that you can run along with that will kind of work through all of these like model training pieces and kind of like the design decisions we made. So I think it's worth running through a couple things and seeing how these things look like inside. Maybe just to, for anyone who does wish to follow along, there will be some setup needed. Let's see if, there's a README here with all these installation instructions. So definitely feel free to follow along. And then after the workshop, if there's any setup stuff needed, I'll come through and we can actually get things set up for people who want to try more immediately. But for now, you can follow along here as well. So there's a little bit of setup done, which is fairly straightforward. So in this notebook, what we're going to do is we're going to train this classifier off of a couple images of Einstein's face. So a couple things to get some faces. And optionally, if you'd like, you can also add in your own faces to the workshop and train your own model for that as well. But for now, this thing will skip it and just use the Einstein images. And then, so now that we have some faces that we're going to use, we're going to basically take these images and then extract an embedding, or maybe map it into an embedding, which better represents the features, the important features of the face. So this thing is where we'll do like bounding boxes over different components of your face. And in this notebook, we also have a a set of negative examples we're going to be using to train the non-match component of the classifier. So we set up our training data, and then we go ahead and train the model. So this stuff is, fairly small data set. The model at its current size can pretty much hit this, like at least on training and test data, pretty much get 100% accuracy. And if we visualize this model, the first thing, the first like kind of naive implementation is a larger multi-layered perceptron than what we did before. So you can see that it's 128 dimensions, 65 hidden layers, or 65 nodes in the hidden layer, and then just one output. And here, even at kind of 128, so in this case, about 8,000 parameters, this can get pretty large and expensive to do in a snark. So what we'll do here is we'll do PCA to extract out a smaller representation, and then see that we haven't lost too much variance on the data set, and then reevaluate and train the model. And in this case, it's still fairly robust enough to get high accuracy on the training and test data. And we see that we have a much smaller architecture here. So the model is much smaller, much easier to transpile into a Leo program, or a program that can be run on the Aleo virtual machine, which will actually go generate a zero-knowledge proof. So in this workshop as well, we've set up a transpiler that'll take a scikit-learn model or a scikit-learn MLP implementation, and then go and transpile that into Leo. So if you get to this point, you'll see that it generates you a program that you can actually go and deploy onto the Aleo network if you'd like to. And yeah, we welcome anyone just to walk through the rest of the steps, but this is the most important piece here, where we've found a digestible model size and encoded it into a Leo program. At this point, any questions so far? Cool. Sweet. So just to kind of recap, the ML model that we kind of landed on was multi-layer perceptron, 32 inputs, 17 hidden neurons, and yeah, fairly straightforward, I'd say very, very basic designs here. Nothing too crazy. I think there is sort of a future direction of work where really you want to be maybe encoding a CNN in this circuit and really overfitting it for your user data. But this is a fairly decent starting point. One subtlety here is that basically a lot of snark systems don't really support floating point, which is needed when you, it's the natural representation for these sorts of computations. So because we can only work with integers, there's a couple different options on how we can kind of go about this process. One way is to do fixed point arithmetic, which is what we which was the approach we go with in this example, where yeah, we basically pick some kind of scaling factor, in this case 16, and then kind of almost hand worked out this number so that you still have numerical stability when you're actually running your computation. Now, this is probably not I'd say there's a much more interesting set of approaches where instead of choosing fixed point representation and still trying to preserve decimals, you can actually just go for some more heavier quantization methods to either do 8-bit ints, even bitnets are pretty solid, and see if those kind of solutions can work as well. Sweet. And then this whole setup we have here basically takes a scikit-learn model and then transpiles it into this programming language that we've built called Leo. And Leo programs are basically compiled down into bytecode that is run on this virtual machine we've built called the AVM, the Aleo virtual machine. And that virtual machine, takes the bytecode, produces constraints, or produces a snark, produces a proof for that model. And finally, there is this kind of question of like hashing. How do we actually commit to a model itself? The AVM also has like instructions for hashing its inputs. So basically, it's actually a very simple setup. You take your model parameters and then hash it with some snark-friendly hash function. And then you have a kind of like unique identifier for your model. We, in this setup, use BHP. But there are much more snark-friendly hash functions. You could go with something like Poseidon and stuff like that. And then maybe one quick thing to comment on is what was really needed for this approach is that because you're only kind of working with like 2 or 3 face samples or signature samples, we need a lot more augmentation to make the training a little bit robust. So for facial recognition, we augment our data set with changing brightness, contrast on the images, and adding noise. And then for signatures, we do rotations and translations on the signature and train off of that augmented data. So at a high level, the app and its like deployment kind of is organized in this way. At the bottom, you have the Aleo network, which hosts the actual program. Then you have the KYA app itself, which is built off of an SDK and relies also on TensorFlow, scikit-learn to do the actual training and model construction. And then you have the Provable repos, which are basically just a bunch of software to help make developing and then running these applications a little bit easier. The main thing to sort of call out here is that on the Provable side, we provide APIs for delegating snark proving to make running these apps a much more humane thing to do in terms of user experience and time. So with this sort of construction, I think like it's sort of kind of up to imagination to see like what new things we can build on top of it. I think like when you start integrating things like live identity into blockchain flows, you have the ability to create stuff that wasn't so easy to do before. So a couple of things that are particularly interesting to me are the ability to oracle in data that has some humanity associated with it. So you could start to maybe oracle in like question and response answers, or even build up data sets of human inputs and outputs, like responses to questions and things like that. Another component is like stuff like institutional payments, where you need a lot of like safeguards before you send out like a ton of money over to another organization. This is where you could actually feasibly design a system that is built on chain and then uses this human-in-loop verification to basically checkpoint and get sign-offs from all of the parties needed, the account manager, the CFO, so on, before actually going and sending off that payment. So it kind of provides the guardrails that crypto doesn't really have right now, where if you have a key, you can pretty much go and fire off things on your own. Here now you can add in extra pieces to like make sure it's not only just having the key, it is also being the person who owned that key. And so all these applications, how do we actually start building out these ideas? There is, in the Aleo ecosystem, we have this language called Leo, which is a domain-specific language for developing smart contracts on the AVM. There's always the question of why another language? Why do I have to learn another thing in addition to Solidity and all this crap? And the fundamental, the real core observation is that ZK is just hard to do and it's fundamentally different. The abstractions that you create for privacy don't naturally fall into, I'd say like standard programming paradigms. You need to treat certain things as first class. So one of these components, one of these things that needs sort of like first class attention is this notion of records, which are encrypted blobs of data. These can totally be like, specified in other languages, but it really is only done as libraries or, and sort of doesn't get the first class treatment that makes it more intuitive to code applications. So we basically went through, like kind of started from ground up and designed a bunch of programming paradigms that will help sort of developers easily kind of specify logic around this stuff. And then one specific paradigm is this like hybrid virtual machine we've created. So the Aleo virtual machine has sort of two modes of execution or two areas of execution. First, some computation happens off-chain, and this is the computation in your snark. And then your AVM code then executes one more time on-chain. And this is execution that's replayed by all of the validators on the network. So in doing so, you have this ability to encode or design an application with a sliding scale of privacy. You choose what you want to put in a snark and make private, and then you can choose what you want to expose, maybe because you need coordination or registry and so on. So the programming language we've designed effectively supports this natively with constructs like records, which are encrypted state, or futures, which are deferred units of execution for on-chain, to be run on-chain. So kind of like roughly, this is how it it looks like, when you're kind of unpacking all that. You have, in your off-chain VM, it can take as input some private data, it's a typo there, some public data as well, and then output some private data, and then also output these things called futures, which are basically deferred units of execution in the sense that there are packets of data that contain a program name, a function name, or a pointer to some code, and the arguments to run the code with. And what this looks like is like, if you guys are familiar with like async programming, these are the results of like invoking an async call in any other sorts of language. You basically get this deferred unit of execution, and then you explicitly await this thing. In our case, you explicitly go and schedule this for execution on-chain. And yeah, with that, we could, maybe this is a good place to take a pause. And before we go into actually integrating some of our these ideas into an authenticated token program, are there any questions so far? Cool. So then we'll do a little bit of live coding just to kind of see how all this stuff looks like. So I'm going to basically unfairly throw you guys into a new programming language. There's going to be a lot of like maybe unfamiliar concepts, but hopefully there's, feel free to raise your hand as soon as like something looks unfamiliar. But otherwise, I'll do more of like a high level overview, and we'll kind of like, available after to, direct you to whatever resources that might be more helpful. But first, it's, I think, worthwhile for us to take a look at what this neural network looks like when encoded as a Leo program. So Leo is kind of loosely inspired by Rust and TypeScript, but still, has its own syntax that will, be unfamiliar for the new user. This program that I'm showing you here has been entirely generated by the ZKML transpiler that we built. So this is entirely program generated, but here we have a couple of data type declarations, which are basically used to encode our model itself. So you'll see kind of like a lot of structs here. The important idea to like just think about is that this is just our way of encoding the model weights into our program. So there's a function here that'll help us, define a model or compute a model hash, which is basically just the hash over all of the parameter or a subset of the parameters in this model. And there's a sliding scale of fidelity here where you can hash more of the parameters to get a more unique identifier over the model. And then to actually go run the model itself, the neural network is encoded here, where you basically just do your linear operations and then your nonlinearity just over and over again until you get your final result. And we just use ReLU as our nonlinearity here. So this program is should be fairly straightforward. It's just does a bunch of additions and multiplications and conditional logic. But then we can use it and use it to encode like a token program that requires facial authentication. So here is another program, authenticated token, which contains our model and then encodes the application, the token logic itself. So if you guys are familiar with Solidity, the AVM also has this notion of mappings, which are key value pairs. And then we can just specify a way of initializing our token and then transferring data or transferring tokens between two addresses. So our initialize function will basically compute a hash of the model, which will be a model of a facial detection model for ourselves, and then initialize to my address or to a given address some amount of public tokens. And then the transfer function will take in our model as well, and then as well as the inputs, and then run the model, and then defer some execution for later, where we check that the model, the outputs achieve some threshold, and then we also go through and actually transfer tokens if it's the case that the model ID matches. So roughly what we're doing here is, in order for me to be able to transfer tokens to people, I need to match the face for my identity here. And this code is available on the Aleo blockchain as well, so it's already been deployed. Here, if you'd like to start working with Aleo, one good place to do it is through the Aleo Explorer. So explorer.provable.com is an explorer that we've built for the Aleo network. If we go to testnet, there are a couple programs for that you could kind of refer to. So for example, authenticated token is a bunch of bytecode here for specifically this program that we just showed a little bit earlier. You can also take a look at the bytecode for the multi-layer perceptron, which is kind of here, and you can see there's just a bunch of multiplications and additions for that program logic. All right. With that, that pretty much concludes everything I have for today. If this is of any interest to you, or if this was intellectually interesting, we'd love to continue the conversation. Either come build with us, or feel free to come up after and we can kind of chat on what we're thinking about for our next steps. I think for us, probably one thing that's on top of mind, or one thing that's really interesting, is to see how we can extend this KYA facial recognition into something more robust. So actually creating larger models that are very, very personally fit and still robust to adversarial examples. And then we can start to assign users a much more kind of robust notion of identity to their sort of like Aleo addresses and their Aleo keys. But yeah, thank you all for listening. Yeah, any questions? I'll also hang around here for a couple minutes, so feel free to, yeah, come up. But yeah, thank you, everybody.